Okay, part B, our second circular motion video, we're going to look at the forces that cause centripetal acceleration. We've only got one more slide for this video, and then we'll get into the final couple of videos on banking angle. So what sort of forces can cause a centripetal acceleration? Well, we saw in the demonstration earlier an example of the tension force. So another example of the tension force might be like if you had a totem tennis ball spinning on a stick or spinning on a pole. The gravitational force, I sort of mentioned before, that might be a satellite spinning around the Earth or orbiting Earth, a bit more scientific word. Or it might be something like the Earth orbiting the Sun. So they would all be examples where a gravitational force causes circular motion. A frictional force could be, well, the most common example of a frictional force is where we're turning on a flat road. So a car turning on a flat road, whether that's driving around a curve or turning around a corner. Okay, we'll explore the next one, the normal force. We're going to explore that in more detail in the coming slides. So that is coming soon. I'm going to leave that one just for now. So at this point, I think it's really important that we reflect on the difference between circular motion that we're looking at in this topic and parabolic motion, which is what we were dealing with in the previous projectile motion topic. Comparing these two often comes up in an exam or a test question, both for this topic, for the motion in two dimensions topic, and also in the electricity and magnetism topic that we're going to explore later on. So firstly, in circular motion, we have a force that is a constant force. At least it's constant in its size, or its magnitude is the word we use a lot for size in physics. So that force is always constant in magnitude, but in a sense the direction is always changing, because the direction is always perpendicular to the direction of motion, or the velocity vector. So I'll just put a V with a vector sign, the velocity vector. However, when we have parabolic motion, the direction of the force is always constant. So when we're talking about gravity, that force is always acting vertically downwards. So if we're dealing with gravity, that direction is downwards in the vertical direction. So if we come back here and look at this, circular motion versus our parabolic projectile motion, the velocity vector here is always, it's not a very good tangent, at 90 degrees to the tangent, and the direction of the acceleration is always at 90 degrees to that and towards the centre of the circle. So where we have, that should be a right angle there, sorry. Where we have a force and an acceleration at 90 degrees to the velocity vector, we get circular motion. However, where we've got our projectile motion, we've got something like this, just represent the velocity vector at a few points. Sorry, this is pretty rough. The acceleration in these cases is always vertically downwards, so that direction doesn't change. So where we have a force field like gravity and later with the electrostatic force that is constant in direction, we get that parabolic motion. We're going to probably reflect onto that in some questions later on, but it's really important that you have an understanding of those two different types of motion, and we learn as we go along where each of them applies and how to identify whether we will get circular motion or parabolic motion. I also should note here, if we want to work out the magnitude, the size of the force causing centripetal acceleration, that we know that force is equal to mass times acceleration, but the centripetal acceleration is given by v squared on r, and mass is given by m. So if you like, our force causing centripetal acceleration is equal to mv squared on r. So we get on our formula sheet Newton's second law, force equals mass times acceleration, and we get that acceleration equals v squared on r. So it's a fairly simple substitution to derive that formula. And we use this formula a bit, and we'll use this in the following slides as well.